Hello students. Over the past couple of lectures, we started looking at pipelining and we started addressing various assumptions that we made to get the pipelining working. And in the last lecture, we looked at the assumption that we made, which is execution of one instruction will not depend on another. So that is obviously not true, and we started looking at the possible dependencies. One was the data dependence and the other is control dependence. And as part of data dependence, we looked at what we can do at the hardware, right? We looked at stalling the pipeline, and other is data forwarding. Let's continue data dependence further. Now we are going to discuss what we can do from the software end, right? Specifically, what we can do at the compiler, right? So the very first question that we need to answer to understand what we can potentially do is can the compiler identify data dependence among the instructions? So data dependence, as you know, is of two types. One is through registers, other is through memory locations. Now the very first question is, can we identify data dependence through registers? Yes, because the register names will be same if two instructions are trying to use it, right? So we can easily identify whether there is a producer-consumer relationship. If we can identify, so can the compiler. In fact, the compiler itself will generate the assembly code, right? So once it generates, it can go back and analyze if there is any producer consumer relationship among the instructions, right? So the answer for this question is yes, if the dependence is through registers. With that, the compiler can figure out dependence among instructions through memory locations. The answer is no, because the exact dependence, if it is there, can only be identified at the runtime. Runtime meaning when we are actually executing the instructions, right? So I gave in the previous class, I gave an example of a load and a store, right? Though when we look at them, both were having different offsets and different base registers, but eventually they can refer to the same memory location. So such dependencies cannot be handled by the compiler because compiler analyzes the code statically, right? So let's see what we can do for the possibility that there is a data dependence through registers. In order to do anything, the compiler needs to have a deeper knowledge of the underlying instruction execution. So what we understood in module 1 was compiler has complete understanding of the ISA, right? Now we'll expect some more knowledge, specifically whether the compiler knows that the underlying hardware has implemented pipelining or not, right? In case there is no pipelining in your uh, process, then the compiler need not worry about data dependency at all, right? Because only one instruction gets executed at any given moment, right? Given point of time. But if pipelining is there, then it also needs to know how many possible stages are there and what are the potential stalls that get introduced if there is dependence among two consecutive instructions or a few set of instructions, right? Some additional knowledge is expected. Along with that, it also needs to know whether at the hardware some functionality like stalling and data forwarding is present or not, because uh, if we build a pipeline that does not have any of these, then the onus is completely on the compiler to make sure that the instructions are spaced enough that there is no overlap in their execution, because the underlying hardware doesn't understand, does not have the hazard detection unit at all. So if I want a simple pipeline which does not take much area or power, right, I'll just discard all these optimizations and say I'm giving the complete job of making sure that dependency among instructions is handled by the software. Then the entire onus will be on the compiler. So only when we have the knowledge of the underlying hardware then alone we can think about possible optimizations by the compiler. There are predominantly two approaches. The very first one is to introduce some dummy instructions, and the second one is to rearrange the instructions. But both of them try to address the question on how the compiler can handle the data dependence. Basically, what it does is, if possible, it will space out the dependent instructions. Let's say instruction 1 and instruction 2 are dependent on each other, means instruction 1 is the producer and instruction 2 is the consumer. At that point, the compiler needs to insert a couple of instructions between them so that when they are executed the hardware, there is no stall, right? So like I said, the very first one is inserting a no-op, which is basically an dummy instruction like add x0 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 x0. In RISC we always store 0. So basically this instruction does not do anything, right? It does not change any other register. It just adds x0 to x0 and writes to x0, right? So you can imagine that there can be a pseudo instruction for this. Now let's look at what the compiler will do when it has this set of 4 instructions. We have ADDI x11 x12 5, ADD x13 x11 x12, ADDI x14 x11 15, ADD x15 x13 and x12. So the very first step that compiler will do is try to see what all dependencies are there. So here we have x11 as the result of ADDI, which is the source of the second, third instructions. So there is a data dependence among instruction 1, 2 and 3. Is that the only dependence? No, because even instruction 2 and instruction 4 are dependent through x13. So looking at these, the compiler can now decide to introduce the dummy instructions. So the very first instruction will remain same, ADDI x11 x12 x5 5. Then we have two no-op instructions. Following that we have the second instruction, which is add x13 x11 and x12. Then we have the third instruction. We space out the third and the fourth instruction with another no-op, right? In this way, when we are running when we are executing these set of instructions, now the 4 instructions became 7 instructions here, right? If you look at how they get executed, when we are trying to decode the second instruction, basically read the values of x11 and x12, the first instruction would be in write back stage. So x11 would already have been updated, which would be read from by the instruction 2. Now the same thing would happen between instruction 2 and 4, right? So because of this additional no-op, by the time we decode the fourth instruction and try to read x13, the second instruction would be in the write back stage and it would have already updated x13, right? So the compiler will try to space out these instructions so that there is no overlap between their writing and reading, right? So if we look at the performance aspect, basically we are trying to execute 4 instructions in the ideal pipeline, we would have expected the instructions would to complete like this. In the fifth cycle, the first instruction would complete, sixth, second, seventh, third instruction, and eighth, the last instruction would complete, right? But if we introduce stalls at the hardware, then we need to introduce two stalls between instruction 1 and 2 and one stall between 3 and 4, right? So that the correct data is given to the consumer. That's what even the compiler is doing at the software. Instead of stalling, it has introduced some dummy instructions. That's the reason the program performance, if you look at it, will not be any better than stalling. So if we look at the cycle of completion, or the cycle in which each instruction would be in the write back stage. So in the fifth cycle, the first instruction will complete. In the sixth cycle, the first no-op will be in the write back stage. In the seventh cycle, the second no-op. In the eighth cycle, the first add instruction would complete. Ninth cycle, ADDI would complete. 10th cycle, no-op would complete. And 11th cycle, the last instruction would complete, right? So this is the reason the performance is same when compared to stalling. So if you ask why are we looking at it, then like I mentioned in the previous slide, maybe there is a simple hardware that does not do any stalling or data forwarding, basically does not have a hazard detection unit. So in that case, the compiler will take these 4 instructions and space them out so that there is no overlap at the hardware. Okay, so this is approach 1. The second approach is trying to rearrange the instructions. Now, what do we mean by rearrange the instructions? So the compiler will analyze the program statically, means it will go and check all the instructions, figure out all the data dependencies, and try to pick those instructions which are safe. Basically, safe meaning which will not break the existing dependencies and will not create new dependencies, and place them in between the producer and consumer instructions, right? So for example, let's take the previous set of 4 instructions. So here we saw that there is a producer consumer relationship between instruction 1, 2 and 3 and instruction 2 and 4. At this point, if the compiler wants to rearrange instructions, let's say it tries to keep instruction 4 between instruction 1 and 2, that will not work because it would break the dependency between instruction 2 and 4, right? Now let's try to see if it can place between 2 and 3. Yes, it can, because there is no new additional dependency that gets created. So the fourth instruction, add x15, x13 and x12 will be before ADDI x14, x11 and 15, right? In that case, there can be a reduction of one stall between basically that will not work because instruction 2 and 4 are dependent. So with these set of 4 instructions, nothing can be done by the compiler. So let's take another example, right? Let's take this sequence of instructions. We have LD x29, 8, x16, subtract x28, x29, x14, SD x28, 12, x16, add x15, x11, x14, subtract x15, x10, x14. Now, if we look at the data dependencies, we have a producer-consumer relationship between the load and subtract instructions and the subtract and store instruction also, right? So, and it so happens that instructions 3 and 4 are completely independent of instruction 1 to 3. So in that case, the best thing that compiler can do can be to move instructions 4 and 5 and place them between 1 and 2. Now the instruction sequence would be 1, 4, 5, 2, 3, right? So in this case, what happens is at the hardware, instead of introducing stalls between the load and subtract, we are executing the add and subtract instructions here. So the number of cycles installs will reduce by 2 in number, right? So that is the reason the program performance can improve when compared to stalling. In worst case, it will be same as stalling. In this example, as you see, if there is a dependency between every set of 2 instructions, then the compiler cannot do anything, right? But if there is a possibility to move the instructions which are safe, then it can do something about it, and even that will reflect as reduced number of stalls. So the example I took has only the arithmetic instructions, right? But things get even more trickier if we have control instructions, right? Uh, the reason being, control instructions will create control dependencies. That's what we are going to see in the next lecture. But for the moment, just ignore the control instructions. Even without the control instructions, the compiler has very limited scope of finding some safe instructions and placing them in between the producer and consumer instructions, right? So with that, I would like to summarize what we have looked at when considering data hazards. At the hardware, we looked at stalling and data forwarding approaches. Stalling is the very basic thing that we would expect the pipeline hardware would do, and data forwarding would be the first line of optimizations that we apply. Both of them would require hardware to detect the dependency and take the corrective actions, right? And at the software, we saw in this lecture that the compiler can potentially analyze the dependencies through the registers and insert some dummy instructions or no ops, or look for some possible safe instructions and place them between 2 dependent instructions, right? And uh, if we try to answer the question, can they both work together? Yes, definitely, because even the pipeline hardware which has data forwarding logic will not eliminate all the stalls, right? So if we have a load instruction followed by any instruction, it would potentially require one stall. But with compiler introducing any safe instruction between them, that stall can be avoided. So the hardware and software solutions, when applied together, can improve the performance further. With that thought, I will pause this short lecture. In the next lecture, we are going to dwell into the control dependence. Thank you.